us a glimpse of arithmetic quantum chaos.
Well, thank you so much. I'm very honored, in fact, deeply touched by the invitation to this great workshop. Actually, the workshop is bigger and the audience is more experienced than I thought. So I'm a little bit embarrassed, especially that, as you may well know, I'm not much of a quantum chaos theorist, not even an arithmetic quantum chaos theorist. But I found that much of my work is inspired or motivated by this subject. So when I was asked to give a colloquium-like lecture, I thought it would be a good idea to give an overview of this subject. So this subject, as it is, comes from mathematical physics, and I don't really have any physics background. So please be easy on me if I make mistakes or when you ask questions. Anyways, I'd like to motivate the discussion with a model system from physics. That is, I will look at a compact orientable Riemannian manifold. I assume orientability so that there is a volume form on the Riemannian manifold. And we consider a particle moving freely on this manifold with unit speed. It's very important that speed is always unit speed. That's the only speed we allow here. And first, in classical physics, we think of the particle as being a point on the manifold moving around. So the formal description of this system in classical mechanics is as follows. The phase space for the system is the unit tangent bundle of the manifold, denoted by Sm here, also called the sphere bundle. And I like to think of this unit tangent bundle as the non-zero tangent bundle divided by the possible scales, that is positive numbers, which I denote by h. H stands for the Planck constant. So I'd like to think of all Planck constants at equal footing. I'd like to make a system that is scale invariant. So each non-zero tangent vector will be scaled onto a unit tangent vector, and that's how I like to think of the unit tangent bundle. So the unit tangent bundle, a point in the unit tangent bundle encodes the position and the speed, unit speed vector of the particle. And so the moving particle can be encoded in a function of time, so a function from R to phase space. And we'll assume that this movement of the particle is smooth in phase space. And then there are various quantities that we can observe about this particle. So we'll talk about bounded observables, which are functions on phase space, that is on the unit tangent bundle, which are real valued and also smooth. These I will call bounded observables because indeed Sm is compact, so these functions are bounded. But for a proper description, yes?
I'm sorry, could you say again what S, T naught?
Sm is the unit tangent bundle of the manifold.
What is T naught?
T naught is the non-zero tangent bundle. So non-zero tangent vectors at points of M. Okay? So, but for a proper description of the system, we'll have to look at also more general observables that I call unbounded observables. So these are functions on the non-zero tangent bundle, also real valued and smooth. These functions can be unbounded, of course. So one prime example of an unbounded observable is the Hamiltonian function or the energy function associated to the system, which assigns to each point in this more general phase space the length of the tangent bundle. Note that usually xi, or the length of xi, is interpreted as the momentum of the particle, so the usual energy function, the usual kinetic energy in this system is usually xi squared, but here I consider xi as the energy function instead of xi squared, so that the derivative of the energy is always a unit vector. So then associated to this Hamiltonian function, there is a system of partial differential equations, the Hamilton equations, which describe the time evolution of the system. And in this case, the time evolution is described by the geodesic flow apparently and the unit tangent bundle, which is the most natural thing that you can think of. So this particle follows its nose, follows its tangent vector, and moves around and carries its unit speed vector with him. And now the role of this modified energy vector is that every tangent vector, even the non-unit length tangent vectors, are carried around by unit speed in this system. So the length of the tangent vector no longer means the size of the speed of a moving particle. Every arrow is carried around with unit speed in this system. And that is in harmony with our identification of the unit tangent bundle with the non-zero tangent vectors modulo positive numbers. So you take like a vector of length 3 that is carried around with unit speed. It's the same thing as if you had scaled down the vector of length 3 to length 1 and you carry it around with speed 1. So that's the classical mechanics system that I'm looking at. It's the geodesic flow on SM with this understanding. In quantum mechanics, phase space, the role of phase space is played by a Hilbert space. I'm sorry, I have some problem with my computer, it's slow. So in quantum mechanics, phase space is the L2 space of M with respect to the volume form of the manifold. It's a Hilbert space in the usual way with the usual scalar product. And then a moving particle is no longer a moving point in phase space, but it is a moving wave. So you can think of a point particle as being a wave with a high peak where the particle is, and then this high peak moves around in phase space, which is now the L2 space. So we usually consider unit length vectors, that is functions of L2 norm 1 in phase space, because the absolute value squared of the wave is interpreted as a probability density of the wave function. That's one interpretation of quantum mechanics. And then a bounded observable becomes a self-adjoint and bounded linear operator on a phase space, usually denoted by op-A. And then an unbounded observable is a more general but still self-adjoint operation in phase space. Now this assignment A to op-A is linear, and it's called quantization. It's not unique, and it comes from physical intuition. But the different quantizations only differ by small operators. I try to say a bit more on that. So usually op-A is realized as a pseudo-differential operator. So a very important special case being when A doesn't depend on the tangent vector, when A is really a function on M independent on the tangent vector, then op-A is always multiplication by A. So the way op-A acts when A is independent of the tangent vector, you multiply psi by that function A. Another extreme is when A doesn't depend on position, it only depends on the momentum. Well, that doesn't make much sense on SM as a whole, but if you take a chart on M on which you can locally trivialize the tangent bundle so that you can think of on a small chart of M the corresponding piece of the unit tangent bundle as a product of a chart and R to the D times R to the D for the tangent bundle part, then you can think of a function that doesn't depend on the underlying points in the chart, but only depend on the vector in R to the D that you choose. In that case, op-A acts on the Fourier side. So you take the Fourier transform of psi, multiply it by the corresponding function that only depends on the velocities, and then you take the inverse Fourier transform. So the mind-boggling picture of quantum mechanics is that this L2 space encodes the whole classical phase space, not only the underlying m, but even the speed information. And the key to this encoding is the Fourier duality, which corresponds to the duality of position and momentum in classical physics. So we have this quantization op A. I will also assume for the purpose of this talk that this quantization is positive. So positive or non-negative functions, non-negative classical bounded observable become positive operators in the quantum phase space. That is, if A is non-negative and you take a wave psi, you let op A act on psi, and you take the scalar product with psi, that scalar product ought to be non-negative all the time. So that makes the later discussion convenient. And then the energy function is quantized in what is called the quantum Hamiltonian. In this case, it is the square root of the Laplace operator. I will always denote by delta the positive Laplace operator, which is sometimes minus delta in some other notations. So I think of delta as being the positive operator, positive Laplace, and then we can take the square root. And then corresponding to the Hamiltonian differential equations is the Schrödinger equation. And then if one looks at the Schrödinger equation, we look at it at the next slide, we'll see that just as in classical mechanics, the geodesic flow describes the time evolution of the system. In this case, there is a unitary flow, a flow of unitary operators, which is nothing but e to the minus it square root delta, which describes how a wave evolves in this quantum phase space. So at this point, it should be clear that eigenfunctions of the Laplace operator are very important to understand the quantum mechanical picture. In particular, because the Laplace operator is self-adjoint, there is an orthonormal Laplace eigenbasis of L2 space that we shall fix at this point as being phi j, and we label the eigenvalues as lambda j. There is the constant function, which has eigenvalue 0, and then we arrange them. The lambda j is in increasing order. They tend to infinity. In particular, each lambda j, each Laplace eigenvalue has finite multiplicity. And then explicitly, the solutions of the Schrödinger equation look like this. So this is how a general wave evolves in time. If you just look at this equation and you plug in 0, then you will understand where the coefficients come from. So psi 0 on the right-hand side is represented as sum of Cj, phi j. That tells you what the coefficients Cj are. And then when you apply the ut operator from the previous slide, these operators act very simply on the phi j's, namely by e to the minus it square root lambda j, where Cj is an L2 sequence. This is how a general wave solution, this is how a particle, a moving particle, a freely moving particle, an M looks like in the wave description, in the quantum mechanics description. And now what is very interesting that these individual pieces, if you look at their absolute values, they no longer change in time. The individual pieces have a separated position and time dependence, and this factor, this time factor, is of absolute value 1. So the density function of these waves is constant. They are stationary waves. So the Laplace eigenfunctions correspond to the stationary solutions of the Schrödinger equation, whose absolute values are 1. So the moving waves can be combined from these standing waves or stationary waves. That also shows how significant these phi j's are. The densities of these phi j's describe the densities or the probabilities of the standing waves that don't move around. And at this point, we can introduce certain very important measures, probability measures, the so-called Wigner measures on phase space, omega j. Namely, because I chose my quantization to be positive, this scalar product is a non-negative linear operator on the space of smooth functions, so on the space of classical observables. So it is given by integration against a unique regular Borel measure. and that's d omega j. So once you fix a Laplace eigenbasis, it comes along with this sequence of Wigner measures that measure, in a sense, how a classical observable, what it is in the jth state of the quantum system. And because I explained that in the case when A only depends on the underlying manifold M, in that case, OP is just multiplication by the function A. The scalar product is nothing but the integral of A times phi j times complex conjugate of phi j. That is to say, on M, these Wigner measures restrict to the more familiar probability densities associated with the Laplace eigenfunctions. So we say that these Wigner measures form a microlocal lift of these classical density measures. And then the motivating question for this talk, or the basic question of arithmetic quantum chaos, is what are the weak star limits of these Wigner measures? So in other words, how equidistributed the phi j's are in phase space. So I prepared some pretty pictures for the sphere and the modular surface, the two main examples featured in this talk. But before getting to them, I'd like to discuss two general features of these Wigner measures, one coming from Weiss' law, the other coming from Egorov's theorem. So Weiss' law says that if you sum up these Wigner measures up to some Laplace eigenvalue bound lambda, then this sum has an asymptotic formula, satisfies an asymptotic formula, namely it is asymptotic to lambda to the dimension over 2 times a constant. The constant has an absolute part, BD standing for the volume of the d-dimensional unit ball, then volume M scaled down by 2 pi to the d, and then it's multiplied by the space average of the symbol or classical observable A. So n lambda A is asymptotic to this quantity. In particular, if you put A equals constant function 1, then this sum is just the usual counting function of Laplace eigenvalues up to lambda, and it is asymptotic to this part of the formula without this integral, because the integral is 1. So that's a generalization of the traditional value. It is a local value and can be proved using pseudo-differential calculus. One important corollary is that in the Cesaro sense, the Wigner measures tend to the normalized Liouville measure d omega. Normalized being normalized meaning that total phase space has volume 1 with respect to this measure. So the Liouville measure is the most natural measure you can put on phase space. Namely, if you take the average of these Wigner measures with lambda j going up to lambda, in the previous notation, that's simply n lambda a over n lambda 1. And that ratio, because n lambda 1 is just asymptotically to this quantity, if you divide that quantity by this quantity, you get the space average, which is just the integral against the Liouville measure. So in the Cesaro sense, the Wigner measures tend to the normalized Liouville measure. So in particular, if the Wigner measures have a limit, then that limit can only be the normalized Liouville measure, because the Cesaro, in the Cesaro sense, it tends to there. But this is also true if we only assume that the d omega j's converge along a subsequence of lambda j's of density 1, meaning that the counting function of the chosen lambda j's is asymptotically the same as the whole counting function, because along such a sequence, n lambda, the new n lambda a and the new n lambda 1 is just asymptotically the original n lambda a and n lambda 1. So this is a very important observation. If the Wigner measures converge for almost all lambda j's, then the limit can only be one thing, the normalized Liouville measure. So that was my short discussion of Weiss' law. The other part that I promised is Egorov's theorem and its consequences. So Egorov's theorem connects the quantum picture with the classical picture. Namely, it examines what is the quantization of a symbol flown by the geodesic flow. So you take a classical observable and you let it flow at time t by the geodesic flow, then the corresponding operator should be much the same as if you had flown the waves by the quantum version of the geodesic flow. That is to say, intuitively, this operator of A composed with GT should be very close, should be equal actually intuitively if the quantum classical transition would be perfect in a sense, then they would be equal. But apparently, quantum physics is different from classical physics, and there is a difference of a small operator. So this small operator is, technically speaking, it's a pseudo-differential operator of degree -1, whereas these are of degree 0, sorry. But let me just say in more down-to-earth ways that this operator is, well, it's obviously bounded. In fact, it is compact, but not only it is compact, but it even remains bounded when you multiply by the highly unbounded operator square root delta. So just read this formula as these two operators being very close to each other. And this has an important consequence, namely, if we integrate, if we evaluate A composed with GT at the jth Wigner measure, it's much the same as A evaluated at the jth Wigner measure. The difference is at the scale of lambda j to the -1/2, which is negligible. Actually, this error term also signifies the possible differences coming from different quantizations. So for all practical purposes, this is 0. This difference is 0 for all practical purposes. Now, this formula is actually very easy to derive from the previous one, namely, these integrals are given by definition by these scalar products, and if you plug in this formula in the scalar product, then well, this part yields this left-hand side, this part yields this one because ut is unitary and acts on phi j by a complex number of length 1, and this operator then produces the error term lambda j to the -1/2. Now imagine that you let j tend to infinity along some subsequence of lambda j's so that the d omega j's have a limit, such in the weak star topology. Such limits are called quantum limits. Then what we find by this equation, this error term becomes 0 in the end, in the limit. So what we find that all quantum limits on SM are invariant under the geodesic flow. So this is a very important observation because remember we had this motivating question, what are the possible quantum limits? And now we see as a consequence of Egorov's theorem that all quantum limits are invariant under the geodesic flow. So at this point you might have the idea, okay, so let's look at all the invariant measures, all the measures invariant under the geodesic flow, and let's try to see which come by as limits, weak star limits of the Wigner measures. Unfortunately, there are usually many measures, too many invariant measures under the geodesic flow, and this classification is very hard to carry out. Okay, so after this introduction, here are some pictures of density plots of Laplace eigenfunctions and the sphere. Now, the standard, so Laplace eigenfunctions and the sphere are really restrictions of harmonic polynomials of various degrees. Here you see 12 eigenfunctions coming from degree 11 spherical harmonics. So they all have the same Laplace eigenvalue, 11 times 12, that is to say 132. Now the full space for this degree or for this Laplace eigenvalue is 23-dimensional, whereas here you only see 12 balls. Why is that? First of all, these 12 balls fit nicely, but more importantly, the missing 11 balls coming from the rest of the basis of the standard real basis just looks like these 11 with a slight rotation. So obviously these real spherical harmonics have a rotational symmetry or partial rotational symmetry. Well, this one is fully symmetric under rotation. It's called the zonal harmonic, whereas these ones have symmetry by pi half, pi over 3, and so on. In fact, there is a very nice formula for these spherical harmonics. In the height variable, it's nothing but a Legendre polynomial, and then this Legendre polynomial is multiplied by a cosine of the rotational angle around the vertical symmetry axis connecting the North Pole and the South Pole. So here you see like the Legendre polynomial multiplied by cosine theta, cosine 2 theta, cosine 3 theta, and so on. So these are the positive and negative bumps of the cosine, 2 positive and 2 negative bumps of cosine 2 theta, and so on. And there are also the sine versions which just look the same, just rotated. In fact, this cosine and its corresponding sine can be combined into a complex spherical harmonic, cosine plus I sine and cosine minus I sine. And this way you get the standard complex spherical harmonics whose density plots look even more symmetric. Namely, the densities are completely invariant under rotation. And there are also other features you can observe in this picture. Namely, this last one. So for every degree there is a last one. These last ones tend to concentrate around the equator, whereas the initial ones tend to concentrate on the North and South Pole. They are all symmetric with respect to the equator, whereas in between there is some other tendency, there are some other hot belts. And where the hot belt lies is described on where you are in this sequence. So you can imagine that you increase the degree and say you always choose the first one in the corresponding sequence of spherical harmonics of that degree, or always choose the last one, or you always choose from the 1/3 position. And then these different sequences of complex spherical harmonics will concentrate on different and well-defined circles at different heights of the sphere. By the way, you can characterize this complex spherical harmonics uniquely as being eigenvalues not only the Laplace operator but also by this rotational operator I d over d theta, theta being the angle, which commutes with the Laplacian. And then because these functions satisfy two commuting differential operators, that specifies the basis uniquely. But if you only look for delta eigenbases, then they are not unique at all. By the way, these operators can be explained from a physics point of view, namely the geodesic flow preserves angular momentum. It preserves angular momentum around any axis, and in this case, the axis featured is the vertical one. And then you can also associate to these density plots some families of closed geodesics in phase space. For example, these spherical harmonics favor the geodesic together with its tangent vectors at the equator, whereas these initial spherical harmonics would correspond to geodesics going through the North Pole and the South Pole, whereas if you choose some intermediate position like this one, they are tilted geodesics as rotated around the vertical axis. So this gives you an idea what the possible quantum limits are when you look at the standard complex spherical harmonics with increasing degree. But there are lots of other bases. For example, take these 12 balls and the missing 11 balls, the 23 balls constituting a basis, and apply 23 by 23 unitary matrix on the basis. Then you get another Laplace eigenbasis, which looks very differently. Actually, that's what I did. I took this 23 times 23 unitary basis, and I got these random complex spherical harmonics. These are true plots. They constitute a part of a basis, actual basis. There is no Heck operator here. No. I just generated a random 23 by 23 unitary matrix, and I multiplied the previous eigenfunctions with it, took the absolute value. No. I didn't do that. I took a true 23 by. Actually, that's why you see these mathematical code credits. The codes for the plots are stolen from Vitaly Kaurov, whereas the sampling from the unitary group U23 is taken from a paper of Maass and Ozols. Anyways, you see very different concentration in these random spherical harmonics as in the previous picture. There are these nice nodal regions and so on. So after these pictures, so now we have some visual understanding of how standards, a nice rotationally symmetric basis looks like, and how random basis looks like. There is this theorem which describes the quantum limits with respect to the standard basis. Actually, these papers are much more general, so it's a bit hard to get this information out of the paper. But what happens that if you look at the orbits in phase space of the joint action of the geodesic flow and this rotation, which is nothing but what I said, take a geodesic with its tangent vectors and rotate it around the vertical axis, then the uniform measure on each orbit, so typically such an orbit is a two-dimensional torus embedded in a three-dimensional phase space. The uniform measure on this orbit is a quantum limit, as I described, by always choosing at the right position from the different degree L standard harmonic spherical sequence. And it turns out that these are all the quantum limits on SM. So this reflects the fact that the geodesic flow on the sphere is completely integrable. So there is another quantity besides energy, namely angular momentum, that is preserved, and that foliates phase space into two-dimensional tori. Well, there is also a one-dimensional one along the equator. So in particular, the Liouville measure is not a quantum limit with respect to the standard basis. And then you can ask what other quantum limits we can get. So at this point, you want to change the basis, and there is this interesting theorem by Jakobson and Zeldich in 1999 that every probability measure invariant under the geodesic flow is a quantum limit if you choose your basis appropriately. But what is the typical situation? What happens for a random basis? And there is a theorem of van der Kam from 97, strengthening a result of Zeldich from 92, that for a random Laplace eigenbasis, the normalized Liouville measure is the only quantum limit. So in other words, the Wigner measures converge in the weak star topology, and then we saw that the limit must be the normalized Liouville measure. Zeldich, so we would say that the random Laplace eigenbasis satisfies has the quantum unique ergodicity property, whereas Zeldich proved the same for almost all lambda j's, that we would say that the random basis satisfies the quantum ergodicity property. Later, it will be clear what it has to do with ergodicity, why it is called that way. Okay, so we discussed the standard basis and the random basis, and at this point, you would like to see some non-random, that is concrete basis that behave more like the typical or the random basis, and for which we shall consider Hecke-like operators or averaging operators on the sphere, take a finite set of rotations, and for each rotation and its inverse, form this sum. So these rotations act on the sphere, hence they act on the functions. And I include R and R inverse to make these averaging operators self-adjoint. Rotations commute with the Laplace operator, so these averaging operators, just like the Hecke operators, of course, commute with the Laplace operator, and we can take phi j to be an orthonormal joint delta T or eigenbasis of L2M. Now, such an eigenbasis will have some special features. First, there is in the same paper there is this interesting theorem by Jacobson and Zeldich, which says that under a mild technical assumption, no quantum limit is supported on a closed geodesic. So at least you can rule out one of the quantum limits in the standard basis picture. However, if R satisfies stronger conditions, one very strong one being that it generates a free subgroup of rotations, then a very recent paper by Brooks, Masson, Lindenstrauss says that at least at the level of M, so the projected measures do converge to the uniform measure along a subsequence of lambda j's of density 1. So in that case, the joint delta T or eigenbases satisfy the quantum ergodicity property. So that concludes my, no, it doesn't conclude my discussion in the sphere. I also still want to talk about Hecke operators to make Philip happy. So just very quickly, there is a similar Hecke theory as on the modular surface, and I attempt to describe it here. Let's identify the square with special quaternions, namely quaternions of trace 0 and length 1. Then each non-zero quaternion acts on this quaternionic sphere by essentially by conjugation, by this formula. And in particular, let's take a maximal order, namely the Hurwitz quaternions so this is slightly larger than, twice larger than the integral quaternions because we also allow half integral entries. And in particular, these quaternions, the non-zero ones, act on the sphere. They act by rotations. But there are some Hurwitz quaternions that we want to mod out by, and those are the units. The unit Hurwitz quaternions. Well, there are 24 unit Hurwitz quaternions. They form the group isomorphic to SLF3. And plus minus 1 acts trivially, so then you get PSLF3, which is isomorphic to A4. And I want to mod out S2, or that's the usual thing to do by the action of these units. A4 describes the symmetry group of the tetrahedron, and it's fun to think about how the A4 group acts by the tetrahedron by rotations. Anyways, there is a nice fundamental domain for this action, which is the very precise analog of the usual fundamental domain for SL2Z on the upper half plane. So in the upper half plane, we have a fundamental domain which is a hyperbolic triangle of angles pi 3, and 0 because there is a cusp. Well, if you wish, you can cut this triangle into two triangles by the vertical axis, and those would be the analogs of these spherical triangles T2 and T1. And even the areas match. This has area pi over 3, 4 pi divided by 12, which is exactly the area of the modular surface. This paper is taken by a very nice paper by McGee. Okay, and once we have this understanding of Hurwitz quaternions and how they act on our model of the sphere, we look at a quotient of the sphere. That's why I featured this fundamental domain. And for an odd prime, odd because 2 is a bad prime, for Hurwitz quaternions, we look at this Hecke operator, which comes from length p Hurwitz quaternions. Actually, in Hurwitz quaternions, there are 24 times p plus 1 solutions of the equation gamma bar equals p, which corresponds to Jacobi's theorem that in integral quaternions there are 8 p plus 1 solutions. That is to say, there are 8 p plus 1 ways to represent a prime p as a sum of 4 squares, but we mod out by the 24 units, so we get exactly p plus 1 Hecke points over which we average with this is a customary scaling 1 over square root p. So the true average would be 1 over p plus 1, but for number theory purposes, it is better to divide by 1 over square root p. And that's how we get our Hecke operators. And these are actually averaging operators in the previous sense, except for the scaling. Namely, you can arrange these p plus 1 rotations into p plus 1 over 2 pairs of rotations and inverse rotations. And in fact, in that case, the corresponding R, so set of rotations, do generate a free subgroup because of unit factorization in Hurwitz quaternions. So this theorem by Brooks, Masson, and Lindenstrauss can be specialized to a single Hecke operator. Very good. And then here is an important result from 2003 by Böcherer, Sarnak, and Schulze-Pilot, which says, well, so these Hecke operators are self-adjoint, they commute with each other, they satisfy exactly the same commutation relations as the classical ones for the modular surface. And then there is an exact formula for the integral over m of the kth harmonics against the jth measure coming from the jth harmonics in terms of a central value of a triple product L function. And if you look at this formula and you analyze what kind of inequality follows from that exact formula, this inequality follows. Here Fj and Fk are the Gergely-Langlands lifts of the mass forms on the sphere. They are holomorphic cuspidal new forms of level 2. The point is that Fj and Fk have the same, exactly the same Hecke eigenvalues as the original forms. So you can think of this triple product L function as coming from these Hecke eigenvalues of the phi j and phi k. Now, the trivial or convexity bound for this L function is apparently lambda j lambda k to the 1/2 plus epsilon. So the convexity bound just fails to capture the decay of these quantities. But if you assume subconvexity for these L functions or even the generalized Riemann hypothesis, then in a very strong sense, you can see that the projected measures on M, so these are not the Wigner measures, these are the projected measures, do tend in the weak star topology to the uniform measure. In fact, it captures an optimal rate of decay lambda j to the -1/4 under GRH for true Hecke eigenbasis of L2M. And now I'd like to switch to the modular surface, finally, which is our favorite, everyone's favorite. I start with some density plots of mass forms. Here I cannot say standard basis or random basis because as far as we know, each Laplace eigenvalue has multiplicity 1, so you cannot combine within a single Laplace eigenspace the various eigenfunctions. In particular, as far as we know, they are automatically Hecke eigenforms. These pictures are taken, my actual slides have larger resolution, by the way. It's just my machine switched to smaller resolution for some reason. They are taken from the L functions and modular forms database. They are publicly available. This is the 1st, 7th, 13th, 19th, 25th, 31st mass form, actually. And later on, there are only even ones, mass forms in the database. So each of them have some vertical symmetry where on the vertical axis you see 0 values. Those are the odd mass forms where not all the values are 0. Those are the even ones. So this is odd, even, odd, 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 even, 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 all the ways even. So at this point, when I saw this picture, I came to the conjecture that these pictures were produced by Fredrik Strömberg. So I contacted him 2 weeks ago and asked him to produce some similar plots for higher eigenvalues. And here are two mass forms, one odd and one even, with Laplace eigenvalue about 1,000. Here is another one with Laplace eigenvalue about 10,000. And here is a third pair with Laplace eigenvalue. The pictures look better in full resolution with Laplace eigenvalue about 100,000. So you can see as the Laplace eigenvalue increases, these, at least empirically, these eigenforms tend to flatten out. And you don't see any of these rotational symmetries as before. But of course, hidden there is lots of symmetry. Well, we see the even-odd symmetry right away, but there are also other hidden number-theoretic symmetries coming from the Hecke operators. We are just not trained by evolution, I think, to see those symmetries. Anyways, in a sense, establishing quantum ergodicity or quantum unique ergodicity is easier because, in a sense, the basis is more canonical. In fact, as far as we know, it's unique. So, in particular, I mentioned that on the sphere, the geodesic flow is completely integrable. Here, the geodesic flow is ergodic. In fact, this was observed for all hyperbolic surfaces of finite volume by Hopf. Here, I attempted to put on one slide the proof of Hopf in a modern way of telling the proof for the modular surface. So this is the proof. Why is the geodesic flow ergodic on the unit tangent bundle of the modular surface? Well, the first observation is that by the Iwasawa decomposition, the unit tangent bundle can be thought of as SL2R mod SL2Z. That's basically because the upper half plane or hyperbolic plane can be thought of as SL2R mod SO2R. So you can think of SL2R over SL2Z as attaching a circle to each point of the modular surface, and that's in effect the unit tangent bundle. And in this model, the geodesic flow acts by right multiplications by diagonal matrices. And now, the geodesic flow being ergodic means that if an L2 function is fixed by the geodesic flow, then it is constant almost everywhere, which is equivalent to saying that it's fixed by the whole group SL2R. So what we want to show that if F is fixed by this special diagonal subgroup of SL2R, then it is fixed by the whole group SL2R. Now, why is that? So we already know that our function by assumption is fixed by diagonal matrices. Let's show that it's also fixed by upper triangular matrices. So let's take an upper triangular matrix. Everything is meant in L2 sense, by the way. So then, by right translations, matrices act on functions. So 1b, 1f differs from f by the same amount in L2 norm as this difference, because here we can replace f by AA inverse f, because AA inverse f is just the same as f by assumption. Now also, this group action is unitary, so if you multiply these two entries by the inverse of this matrix, then you still get the same difference. But if you calculate this matrix, then it's another upper triangular matrix with entry b over a instead of b. And if you let, well, we think of b as fixed, but we can play with a. If you let a tend to infinity, then this matrix tends to the identity matrix, and the group action is continuous. So in the end, this difference tends to f minus f, which is 0. But this difference is just constant. It's not moving anywhere. A was an artificial parameter. So in the end, this must be 0. It was 0 all the time. So this shows that if a function, L2 function, an SL2R mod SL2Z is fixed by diagonal matrices, then it's also fixed by upper triangular matrices. By a similar argument, it's also fixed by lower triangular matrices. In the end, the whole group fixes F. And then basically by the uniqueness of Haar measure on SL2R, you conclude that F is constant almost everywhere. And this has an important consequence, namely the so-called quantum ergodicity theorem by Schnirelmann, Colin de Verdier, and Zeldich says that once the action of the geodesic flow on phase space is ergodic, almost all Wigner measures tend to the uniform Liouville measure. So no matter how you choose your basis, d omega j will tend to d omega in the weak star topology along a subsequence of lambda j's of density 1. Famous quantum ergodicity theorem. So that's why it is called quantum ergodicity theorem or quantum ergodicity property, because it has so much to do with ergodicity. And here is the proof again. Try to make it as informative and as concise as possible. Namely, let's take a symbol A. Without loss of generality, we can assume that its space average is 0, because you can always subtract the space average. And then we want to show that when we integrate this symbol against the Wigner measures, almost all of them tends to 0. Well, there is a subtlety here that I will mention at the end, but that's our principal goal. And at this point, we need to bring in the ergodicity of the geodesic flow. So let's consider a fixed time average of our symbol. So we flow by the geodesic flow, and we average these flown values. So we take a time average. Now, ergodicity connects the time averages with the space averages. That's the idea of the proof. Let's look at the average of the squares of the integrals we are interested in. By the Egorov theorem, nothing changes in the limit when a is changed to some translated copy of it for a fixed small t. So for our fixed capital T, nothing changes when a is replaced by its time average. Well, there is a smaller one error coming from the error term in Egorov's theorem, but in the limit it will tend to 0. And then we simply apply Cauchy. So at this point we apply the Egorov theorem that I discussed before. And then we can apply Cauchy-Schwarz very simply. And at this time we can apply the Weiss theorem for this sum and get that these integrals in Cesaro mean tend to the space average of the time average symbol. And I want to make this less than epsilon for lambda sufficiently large. How can I make this less than epsilon? Well, first of all, I can choose depending on epsilon and t so that this is less than, say, epsilon over 2. That's because of Birkhoff's theorem, and this is where we use that the geodesic flow is ergodic. And then depending on this t, which in the end depended on epsilon, there is a lambda sufficiently large so that this is also less than epsilon over 2. And so this way, in the end, depending on epsilon for lambda sufficiently large, this average is less than epsilon. So in fact, this left-hand side tends to 0 as a whole, which means that depending on A, there is a sequence of lambda j's of density 0 outside which we see that these integrals tend to 0. So, well, at this point, we see exceptional sequences depending on the symbol, but then a diagonal contour-like argument, you can take a union of the various, or you can sieve one by one the full sequence of lambda j's to get, in the end, a true sequence of lambda j's of density 1, which works for all A uniformly. Okay, and so once we discussed the ergodicity and the quantum ergodicity theorem, it's time to talk a bit about the quantum unique ergodicity conjecture. So in this conjecture, we assume that M has a negative sectional curvature, and we still take any orthonormal Laplace eigenbasis. Under this assumption, the famous Anosov-Sinai theorem from '67 says that the geodesic flow is ergodic. In fact, it is much more chaotic than ergodic. It's an Anosov flow, which probably motivated Rudnik and Sarnak to state their famous quantum unique ergodicity conjecture, saying that there is no exceptional sequence of Wigner measures tending to anywhere but the normalized Liouville measure. That is to say, the normalized Liouville measure is the only quantum limit on phase space. Concerning this conjecture, I know about two general results. One is a recent theorem by Anantaraman saying that every quantum limit has positive entropy for the geodesic flow. And another theorem by Hassel and Hilaire from 2010, which I informally formulate for the purpose of this talk, as to it's not enough to assume that M has non-positive curvature and an ergodisic geodesic flow on its unit tangent bundle. So if you slightly weaken these conditions, then you can produce contour examples. So the contour examples displayed in the paper are Riemann surfaces of higher genus, which have some large cylindrical part embedded in it. So there is a large part of phase space for these surfaces on which there is a periodic action of the geodesic flow. And even though this part of phase space is of 0 measure, it is sufficiently large to destroy quantum unique ergodicity. But of course, unique quantum ergodicity still holds. And I have 2 slides left for the remaining few minutes, which is about arithmetic quantum unique ergodicity on the modular surface. So here I define the usual Hecke operators. SL2R acts on the upper half plane by fractional linear transformations, and then out of determinant P integral matrices modeled by determinant 1 matrices, I can form P plus 1 Hecke points just as before on the surface and scale them with the usual 1 over square root P factor. This is a beautiful family, commuting family of self-adjoint operators commuting with the Laplace operator, and we can choose a Hecke eigenbasis consisting of Laplace eigenfunctions which are at the same time eigenfunctions of all the TPs. And then, corresponding to the theorem of Böcherer, Schulze, Pilot, and Sarnak, the celebrated thesis of Watson established a similar estimate for the integrals of harmonics with respect to these harmonic probability measures on the underlying manifold. Same formula and same decay rate as implied by subconvexity, which is not known yet, or GRH, or the generalized Lindelof hypothesis. So we have very good reason to believe that arithmetic quantum unique ergodicity holds on the modular surface with a very good decay rate, namely lambda j to the minus 1/4. Now what's very astonishing that Lindenstrauss in 2006, together with the supplemental result of Sandra-Rajan in 2010, managed to establish the arithmetic quantum unique ergodicity conjecture, not with the decay rate, but effectively the conjecture on the modular surface, or in fact on any arithmetic hyperbolic surface. So I don't have time to go into any of the ideas of this magnificent work. Let me just say that there is a lot of number theoretic input that goes into the theorem. In particular, nice calculations with Hecke eigenvalues. Similar, actually, than in related problems like the subnorm problem, in amplification method, and so on. And the very recent result that I learned actually while preparing for this talk is that a single Hecke operator suffices for this theorem. So you don't have to assume that phi j is a delta eigenbasis with eigenfunctions consisting of eigenfunctions for all the Hecke operators. It's enough to assume that phi j's are only eigenfunctions of the Laplace operator and a single TP. That's already enough to ensure that, at least at the level of the surface, the d mu j's tend to the uniform distribution. That's it. Thank you very much for your attention. No, I'm not. It would be nice, but well, the sphere pictures were produced by me, but by someone else's code. I'm not a great programmer, and these pictures were produced by Strömberg. Maybe we should pursue him to do nice Hecke plots on the sphere. I think he can do it, and we should ask him. Yeah, I agree. It would be nice to have those pictures. Thank you so much.